Hi class! In this video, we are going to review the formulas and how to calculate the values needed. Also, we will see how these topics, like Coulomb's law, electric field, force, work, electric potential energy, electric potential, and electric potential difference are related to each other. Let's first review the formulas from our previous lesson, starting off with Coulomb's law. The electric force or the electrostatic force. The formula is this one. F, which is force or the electrostatic force. K is the Coulomb's constant. Q1, particle charge 1. Q2, particle charge 2. And R is the distance. Next is electric field. As we all know, electric field is defined to be the amount of electric force per charge exerted at that point and in space. And the formula for electric field is this one. E is the electric field strength or intensity. F here is the force. The force that is being experienced by the test charge. And Q, the small q here, is the test charge. Now force is found using Coulomb's law. Take note that force can be found using the Coulomb's law formula. The force or the electrostatic force. Now this one is the formula. Q1 is the point charge and Q2 is the test charge. Q1 in other formulas is represented as capital Q. Applying the formula of force to electric field, so electric field is equals to force over charge, the Q. Now the force could be replaced using the Coulomb's law's electrostatic force formula. So as you can see, we applied the formula for force and the Q or the test charge was cancelled out, leaving only the bigger Q, which is the charge or the point charge. So electric field or the formula of electric field is now E is equals to Coulomb's constant times point charge over the distance squared. And the unit is Newton per Coulomb. If we have a sample problem and the value of electric field and test charge are given, we can use this formula to compute the value of force. Now F is equals to the test charge times the electric field. And we have already encountered these problems before from our past lessons, so just kindly review your lectures and notes that you have written from our past lessons. Let's move on to work. Work is a product of the magnitude of the displacement of an object and the component of the force parallel to the displacement. So product of displacement and the parallel applied force. Now the formula for work is this one. Now work is equals to force times the distance. And work is in joules. And the applied force, of course, in Newton, and the distance in meter. Take note that the formula of work can be like this. Work is equals to force times distance times cosine theta. If there is an angle given, use this formula. So cosine theta, angle between the force and the displacement. Again, take note that work is measured in joules, and joules are used as units for energy. So what is energy? Energy is the ability or capacity to do work. Potential energy is the energy that could be used to do work. Again, energy that could be used to do work. It is the energy due to position. Now let's find out what is the relation of work, energy, and potential energy to our main topics. First is electric potential energy. Electric potential energy is the energy that is needed to move a charge against an electric field. The electric potential energy describes how much stored energy a charge has when moved by an electrostatic force. Take note, when work is done by electric field, change in electric potential energy occurs. To define the electric potential energy, a reference point must be defined. But before we proceed further to electric potential energy, let's see first the connection of work to electric fields. Now, in a constant electric field, when a charge is moved by a distance, the electric potential energy would be like this. Work, again, the formula is equals to force times distance. And for a constant electric field, the force is equals to charge times the electric field intensity. Now, the work done by the electric field on the charge is this. And the formula would be transformed into this one. Work is equals to the charge times the electric field intensity times the distance. Now, this is the work done in moving a charge from point to point in an electric field. Now, let's see the connection of work to electric potential energy. Since electric potential energy is the energy needed to move a charge, just like potential energy, the energy needed to do work, electric potential energy is the energy needed to move a charge. And work is done when a charge is moved from one point to another in an electric field. Now, using the formula of work, work is equals to force times distance, and using Coulomb's law for electrostatic force, we are going to replace the formula for force into the Coulomb's law. Now, the formula is like this. As you can see, the distance that is represented by letter D was replaced into letter R. Take note that D is equals to R. They are both representing distance. Now, using the formula, we can cancel the square of the distance, leading us to this formula. U now represents the electric potential energy. So W, which represents work, is now replaced to U, which is the electric potential energy. Electric potential energy is equals to the Coulomb's constant times the charge that creates the electric field, which is the point charge. And the small q is the test charge over distance from the reference point. Now the point, or one point, to another. Now let's try a sample problem for electric potential energy. What is the potential energy if a positive 2 nanocoulomb charge moves from infinity to point A, which is 8 centimeters away from a positive 6 microcoulomb charge? As you can see from the illustration, we have there a point charge, which is represented into capital letter Q, and a test charge, which is represented by small letter q. Now, the q here, the small letter q, is positive 2 nanocoulomb, or simply 2 times 10 raised to negative 9 coulomb. And the point charge, which has a value of positive 6 microcoulomb, which is also equals to 6 times 10 raised to negative 6 coulomb. Now, the 8 centimeters here should be on the black arrow. This one is black arrow, because this charge, based from our sample, the q here, the small q here, is the charge that came from infinity and then moved to point A. So it is from infinity, somewhere from infinity, then it moves to this point here, point A. And point A is said to be 8 centimeters away from the point charge. Now, we are asked to find the potential energy, or more specifically, the electric potential energy. Okay, so the solution, using the formula, U is equals to K, the Coulomb's constant, times the point charge, times the test charge over the distance. Now, using this formula, apply the value. So we have there the constant the constant or the Coulomb's constant, times the value of the point charge, which is 6 times 10 raised to negative 6 Coulomb, times the 2 nano Coulomb, or 2 times 10 raised to negative 9 Coulomb, over the distance. Take note that the distance given was in centimeters, so you have to convert it into meters. So we have 0.08 meter. Now, using your calculator, kindly check if you get the final answer. So the final answer, the electric potential energy, is 1.35 times 10 raised to negative 3 Newton meter. And take note that Newton meter, the unit for Newton meter, is equals to joules. So we can use joules as a unit for electric potential energy. We can also use prefix multipliers like this one. U is equals to 1.35 millijoules. So milli here is equals to times 10 raised to negative 3. Now let's move on to electric potential. Now take note that electric potential energy is different from electric potential, but they are both related to each other. Now electric potential is the amount of work needed to move a unit of charge from a reference point to a specific point inside an electric field. The amount of work done by bringing a positive charge or test charge from infinity to the point charge. Now, electric potential, represented into letter V, is defined as the electric potential energy, which is U, per unit charge, which is represented by letter Q. Now, V is equals to U over Q, and the unit for this is joules per Coulomb. Now take note that joules per Coulomb is equals to volts. Okay, so V here is the electric potential, joules per Coulomb, or simply volt. U is the electric potential energy in joules. Q is the test charge, which is represented in or has a unit of coulombs. Now, note that electric potential has the unit of volts. Now, 1 volt is equals to 1 joules per Coulomb. Now, electric potential is related to both electric potential energy and the electric field. Since electric potential is equals to electric potential energy over charge, we need to apply the formula for electric potential energy. So, replacing U into the formula of electric potential energy, the formula for electric potential would be like this. So once we apply the formula of electric potential energy, the test charge, Q, the small q, will be cancelled out, giving us this formula. Okay, so V is equals to K times Q, the big letter Q, over R, where V here is the electric potential, K is the Coulomb's constant, the capital letter Q is the point charge, and R is the distance. So this is the final version of the formula for electric potential. Take note that potential due to positive charge is positive, and the potential due to a negative charge is negative. Meaning to say, always use the sign of the charge. So when we calculate the values, we have to always include the signs of the charge. Unlike our previous lessons when we computed the Coulomb's law, the values of the force on Coulomb's law, we usually disregard the sign. But for this case, for potential energy, rather, not potential energy, but for electric potential, for both electric potential energy, electric potential, we need to use the sign. If it's negative, negative. If it's positive, positive. So we have to write it down when we compute it. Let's have a sample problem for electric potential. Number 1. A charge of 6 times 10 raised to negative 7 Coulomb is transferred from infinity to point A. If the work done to do this is 1.2 times 10 raised to negative 5 joules, what is the potential at point A? So the given values is Q, which is the charge, which equals to 6 times 10 raised to negative 7 Coulomb. Work here can be equal to the electric potential energy, which is equals to 1.2 times 10 raised to negative 5 joules. And we are asked to find the potential or the electric potential. Okay, so using the formula, the original formula, which is electric potential equals to electric potential energy over charge, apply the values. So we have 1.2 times 10 raised to negative 5 joules over 6 times 10 raised to negative 7 coulombs, leading us the final answer of 20 joules per coulomb, or simply 20 volts. Again, joules per coulomb is equals to volt. So we are going to use volt for electric potential. Let's try another problem. Number 2. Find the potential at a distance of 6 centimeters from a negative 5 nanocoulomb charge. Now the given values from the problem is a distance and a charge. So in order to compute the electric potential, we're going to use the formula, the final formula for our electric potential, which is V equals K times Q over R. Now, based from our given, we only have distance and the charge, so we're going to use this formula. So the given R is 6 centimeters. It is the distance, and the distance should be in meters, so you have to convert it. So it's 0.06 centimeter. Oh, no, meter. Okay, so it's meters, in meters. And then Q is equals to negative 5 times 10 raised to negative 9 coulomb. Again, take note, nano is equals to 10 raised to the negative 9. And then, of course, our Coulomb's constant, which is 9 times 10 raised to 9 Newton meter squared per Coulomb squared. So kindly erase the value for the centimeter. Again, it is 0.06 meters in meters. Now, we are asked to find the potential, electric potential. Now, using the formula, so let's compute Coulomb's constant times the charge, which is negative 5 times 10 raised to negative 9 coulomb over 0.06 meter. Now, leading us the value, a final value of negative 750 Newton meter per coulomb. And Newton meter, again, is equals to joules. So it would be joules per coulomb. And again, joules per coulomb is equals to volts. So the final answer is negative 750 volts. So that is the electric potential. Now let's move on to electric potential difference. Now, electric potential difference is the difference in electric potential between the final and the initial position when work is done upon a charge to change its potential energy. So the formula is here. Change in V. Now this triangle is change. It means change. In V, change in electric potential is equals to the final electric potential minus the initial electric potential. So this is the electric potential difference. Vf is the final position and the Vi is the initial position. So let's have a sample problem for electric potential difference. Number 1, a point charge of negative 6.00 times 10 raised to negative 9 coulomb is 3.00 meter away from point A and 5.00 meter from point B. Find the potential at point A and at point B, And what is the potential difference between points A and B? So we are given charge, Q, specifically the point charge, which is -6 times 10 raised to -9. And then a distance A, 3.00 meter, and distance B, 5.00 meters. So we are asked to find the electric potential for point A and point B, and also the electric potential difference between the 2 points. Now, using the formula for electric potential, first let's compute the electric potential for A and B. So using the formula, V is equals to K times Q over R. So we have there the Coulomb's constant times the point charge over the distance of A, point A, which is 3.0 meter, giving us the value of -18.0 volts. Now for point B, using the same formula, apply the constant of Coulomb's, or Coulomb constant, times the point charge over the distance for letter B, or point B, giving us the value of -10.8 volts. Now, we have the value for both A and B, the potential, or the electric potential of A and B. Now we can compute the electric potential difference of point A and B. Now, using the formula, electric potential difference is equals to the final position, which is the potential B, minus the potential A. So it is equals to -10.8 volts minus -18.0 volts, giving us a final value of 7.2 volts. Now this is their difference. The electric potential difference of point A and B is equals to 7.2 volts. Let's try another example. This time, I want you to use your calculators and try computing it by yourself. Okay, so we have here a point charge of a positive 1.6 times 10 raised to -19 Coulomb is 2.5 times 10 raised to -11 meters away from point A, and 4.2 times 10 raised to -12 meter from point B. Find the potential, electric potential, at point A and point B, and what is the potential difference. Now we have here an illustration plus the given. So we have there the point charge. As you can see, this one is the point charge. It is positive 1.6 times 10 raised to -19 Coulomb, and its distance from the point charge to point A is 2.5 times 10 raised to -11 meter, while its distance from point B, this one, is 4.2 times 10 raised to -12 meter. Now we are asked to find the electric potential for A, point B, and we are asked to find the potential difference between the 2 points. Now using the formula, we can solve the potential, the electric potential of A and B. So the formula is, of course, again, electric potential equals the Coulomb's constant times the charge over the distance. So point A, we have the Coulomb's constant times 1.6 times 10 raised to -19 Coulomb over 2.5 times 10 raised to -11 meter. So kindly check on your calculator if you get the same answer. And the final answer for this is 57.6 volts. So for potential A, it is 57.6 volts. Now for potential B, electric potential B, apply the same constant, Coulomb's constant, times the charge. Okay, so it's 1.6 times 10 raised to -19 over 4.2 times 10 raised to -12 meters. Now take note, this is distance for the point B. Now kindly check on your calculator if you get the same answer. The result is 34.3 volts. Okay, now that we have the value for both points, the potential, the electric potential of A and B, we can now compute for the electric potential difference. Now, as you can see, the final position here is B and the initial position is A. So, by applying the formula of electric potential difference, which is equals to the final electric potential minus the initial potential, okay, so we have here 34.3 volts minus 57.6 volts, giving us in an electric potential difference of negative 23.3 volts. So kindly check again on your calculator if you get the same answer. So that's it. Thank you guys for listening. I hope you learned something from this video and hope to see you soon. Bye!